Good morning, everyone, and welcome to today's webinar. My name is Kira Proctor, and I'm the Managing Director of the Proctor Group. And today, we're going to look at strategies to manage moisture and energy in off-site and modular construction, and what functions construction membranes can play in delivering effective solutions, both on-site and off. As usual, we'll follow up with a Q&A session, so any questions you have for our team, you can type them into the chat box here, DM us at Proctor Group, or email webinar@proctorgroup.com. At the Proctor Group, we've collaborated with modular and offsite companies for many years. Whilst we've encountered challenges alongside our customers, we have also witnessed numerous successes within the sector. We aim to showcase success stories from the offsite sector and emphasise how customers have effectively navigated and overcome recurring modular design challenges. With growing demand and government targets for new construction increasingly conflicting with shortages of the skilled labour necessary for delivery, moving construction off-site can offer a compelling solution. Whilst there will always be a place for highly skilled trades, factory-based production techniques can have a significant impact on efficiency, speed of construction, and simplifying a move to the closer manufacturing tolerances required to deliver cutting-edge building envelope performance. With the construction industry facing the challenges of skills shortage, could the modular and off-site sector be the solution? Through the integration of modern technology and the advantages of better factory environments, modular construction offers a compelling alternative to the cold and wet conditions of traditional site work. This mix of efficiency and quality is made possible by the principle of design for manufacturing and assembly, or DFMA. This is an approach based on high-volume manufacturing techniques utilised across a wide range of industries. The key to this approach is simplifying and streamlining the design of a building, considering the actual process of fabrication. This helps to ensure the designer's goals and requirements are met, not by strictly enforcing complex specifications through micromanagement, but rather by designing out opportunities for problems to arise. Put simply, there's no way to cut corners if the path is a straight line. In this context, the consistent performance offered by construction membranes and the factory-based assembly typical of modular construction can be combined to produce highly effective and optimised results in 5 key areas. Firstly, by facilitating standardisation and repeatability of manufacture, where membranes can be easily applied to modules and panels in a factory setting with standardised detailing for joints, openings and service penetrations. Such a simplified design greatly increases the ease of assembly, with the need for complex installation and detailing on site greatly reduced. The controlled environment of a factory also reduces the potential for weather-related delays or problems. The ability to integrate installation of services and building systems also facilitates better integration of services into the design and installation process. This reduces the need for skilled labour on site and the potential for rework or correction of problems. The net result of this simplified and optimised process is higher construction quality and less variation in the as-built and as-designed performance of the building envelope. This in turn means tighter tolerance and better efficiency target can be adopted throughout the process, while still ensuring compliance with regulations and quality targets. Quality can be significantly enhanced with off-site construction. Each process of the manufacturing line can be meticulously documented, making it easier for warranty providers and construction inspectors to review. Inspections within a factory setting are more straightforward, as every process is visible and controlled, compared to the complexities of walking around a traditional building site with numerous homes. This integrated and optimised construction process fits well with the similarly holistic design principles outlined in the latest edition of the BS 5250 Code of Practice for Moisture Control in Buildings. First introduced in 1975, BS 5250 originally focused on condensation in buildings. However, since then it's become more widely recognised that a more wide-ranging approach to dealing with moisture control is beneficial. This approach was outlined in detail in the 2017 BSI White Paper, Moisture in Buildings: An Integrated Approach to Risk Assessment and Guidance. This approach was formalised in the 2021 edition of BS 5250, which both emphasises the need to develop a full understanding of the range of moisture risks present in the building envelope and outlines the key tools and strategies required to implement this. Developing this holistic approach to managing heat, air and moisture and using construction membranes to optimise performance is a key part of what we do here at the Proctor Group, and we've long recognised the importance of a well-considered and integrated approach. To fully understand how to best manage these factors, there are three key high-level design factors we need to address: the building, the weather and the occupancy. The first and most important part of this is the building occupancy, its purpose and function. This is what contributes most to the temperature and moisture conditions that the building fabric must accommodate, and the in-service moisture risk. A warmer and humid environment, such as a swimming pool, or higher occupancy, such as a theatre or cinema, will present a higher risk than a typical dwelling, which in turn is higher risk than a storage space or warehouse. The challenge with modular system design is to be able to accommodate as wide a range of moisture scenarios as possible without modifying the core specification. Whilst a one-size-fits-all approach is rarely a good strategy, with careful consideration the performance window can be widened and optimised to fit a broad range of occupancy pattern without significant alterations to the specification. Much like the occupancy of the building determines the internal environment conditions and resultant moisture risks, the weather determines those conditions and risks externally. As with internal conditions, an appreciation of the variety of conditions that must be allowed for is important. For example, the Passive House Planning Package divides the UK into 22 different climate zones, reflecting the variations in temperature, humidity, rainfall and wind speeds that can be expected even across a relatively small distance. As well as the weather during service, it's also critically important to consider weather during transportation and storage of modules, panels and other materials. If weather during storage contributes to the moisture load significantly, it can be difficult for this additional moisture to dry out if not anticipated and accounted for at the design stage. Once we have a good appreciation of the internal and external environments, it's possible to begin to design the fabric of the building to work within these parameters. Once again, we need to understand the interactions between materials and their purposes to ensure the design is properly optimised. Concrete and masonry buildings typically have higher internal moisture loads than timber frame, as there's more wet trays to dry out. But if not stored correctly, a timber frame can absorb significantly more moisture than may have been anticipated. For off-site construction, which in theory has very low initial moisture loading due to factory production, this can be an important consideration. If modules or panels become wet at any point during production, storage or transportation, this should be accounted for, as the fabric may not be capable of allowing the elevated moisture content to dry sufficiently quickly to prevent problems arising. Such problems can be exacerbated by non-permeable protective measures such as shrink wrapping, which will trap any moisture present. Whilst this might not seem like a big problem, if materials are stored for a long period of time, this trapped moisture can lead to mould growth in the stored materials. In our experience, most modular design challenges arise during the storage and transportation stages. At the Proctor Group, we conduct hygrothermal assessments, not only on the finished building, but also on the modules in their storage state. This is crucial because modules in storage may be in a completely different climate zone compared to the site location, or they may not yet include the complete build, such as external insulation or cladding systems that are yet to be added. From these high-level factors, we can then begin to break our assessment down into the low-level interactions between the heat, the air and moisture, and we'll now move on to consider how we can assess, model and test these both at the design stage and on-site. Heat flows through the building fabric in three main ways. The first of these, conduction, occurs via a direct physical contact between materials, and this is what insulation materials typically reduce. The second, convection, occurs through a fluid medium, in this case usually air, moving around the building. Gaps, cracks and other imperfections can allow air movement to transport heat out of the building, bypassing the insulation layers. The third, radiation, transfers heat directly through infrared waves and requires neither contact nor a fluid to transfer heat. This type of heat loss is reduced by using reflective foil membranes and insulation facings. We can calculate how much energy is lost by conduction and radiation using U values, which is a measure of how fast heat flows out of the construction. To determine this value, we first look at the thermal conductivity, or lambda value, of the insulation. This shows how well a material transfers heat and does not vary with thickness, which makes it a good way of comparing how well materials work as insulation. If we divide this value by the thickness of the insulation layer, this gives us the thermal resistance, which is how well the material restricts the passage of heat. To arrive at the U value, we can then add together the thermal resistance of each layer in the construction and take the inverse of that value. Finally, we must apply corrections to account for areas where the insulation is intersected by fixings or structural members. This is called thermal bridging and can arise, for example, when a metal stud which conducts heat well passes through a layer of insulation. Corrections are also applied for fixings and for any air gaps that may be present. We need to account for these air gaps, as this is one way to determine the effect of convection on the overall heat loss. Another important component of convective heat loss comes from the wind acting on the building, with cold air pushed into the building on the windward side, called infiltration. Conversely, on the leeward side, the reduced pressure draws warm air outwards. A similar process occurs with warm internal air rising upwards through the building, drawing colder air into the heated spaces. Both sources of heat loss can be reduced by the installation of an airtight layer in the building, with air barrier membranes being the most common way to achieve this. The degree to which this air movement affects energy performance depends on the flow rate. In the UK, this is typically expressed in cubic metres of air movement per square metre or floor area per hour at a pressure of 50 pascals. This value is used in energy performance calculations to determine the energy input required to overcome these losses. To verify the value used in the calculations is correct, buildings are pressure tested by either pushing air in or drawing air out to achieve the 50 pascal pressure difference between inside and out. The building regulations specify a backstop value which varies across the UK regulations, but is typically around 7 to 8 metres cubed per square metre per hour. The passive house standard is considerably tougher to meet, at less than 0.6 air changes per hour, which is roughly equivalent to the gap the size of a 5-pence piece for every 5 metres of floor area. Improving overall heat loss in any design is crucial, but it's especially important in modular construction. In this sector, wall thicknesses play a critical role in costings, transportation, and performance. Optimizing wall thickness can lead to better thermal efficiency, reduced costs, simplified transportation, and enhanced overall performance of the modular units. Both the U values and the air leakage rate are used to calculate the overall heat loss, and hence CO2 emissions, so it's possible to look at how these two factors interrelate. Using a simplified example, we can see that achieving a performance uplift of just under 7% requires the wall U values to go down from 0.15 to 0.05, or the air leakage rate to reduce from 7 to 0.5. But what do these solutions look like in practice? Our base wall with a 0.15 U value would look something like this: a 95mm SFS wall with an infill of mineral fibre and a further 175mm of fibre externally. This type of construction will typically achieve an air leakage rate of around 7 with no special measures taken. To get this down to a U value of 0.05, we would need to increase the thickness of the external insulation layer to 630mm, which is obviously not practical. This is because U values are not linear, so as the U value decreases, insulation becomes exponentially thicker. If we instead reduce the air leakage rate, this doesn't add any thickness, but requires a more careful approach to the air barrier layer. If this was done using an air and vapour control layer, an AVCL, internally, this would require careful sealings of all laps and joints and of all service penetrations and runs. Whilst this is by no means impossible, particularly in a factory setting, it does require a degree of additional time and skill to achieve this, and is susceptible to damage should any follow-on work on site be required. If we move to using a self-adhered air barrier like Wrap-Tite, the air barrier moves to the external side of the panel, away from most of the surfaces and potential penetrations. As well as requiring less sealing in the factory, this configuration also means any adjustments or alterations to the surfaces, either during construction or throughout the lifetime of the building, can be made with less risk to damage the airtight layer. A fully self-adhesive membrane also means the air barrier is firmly supported by the substrate, making it more durable during transportation and temporary exposure. Wrap-Tite uses a vapour-permeable adhesive, which provides a secure and permanent bond once fully cured, but which allows for repositioning during the installation itself. This helps ensure a high-quality installation with no gaps or wrinkles. Because the full surface of the membrane is adhesive, this provides a greater area for adhesion. This will result in a stronger bond which is more resistant to any surface defects or contamination when compared to a tape joint which has a much smaller bonding area. The use of an external air barrier is just one of the situations where construction membranes are useful in optimizing the design of an element. By introducing reliable and repeatable performance, properly installed membranes can help us ensure the variation between design calculation and on-site performance is minimized. We supply a range of membranes with varying performance characteristics, so it's important to know which material is used where within the construction. For this, we use a condensation risk analysis calculation to model the movement of moisture through the construction. This type of calculation uses the properties of the materials in a construction and the internal and external environment conditions to first work out the temperature gradient throughout the structure, then to work out the point at which moisture vapor will condense back into liquid water, known as the dew point. If these lines coincide within the construction, there is a risk that moisture could accumulate and lead to damp and mold growth. By adding membranes to the construction, we can alter where the dew point occurs to ensure no risks are present whilst allowing the wall to breathe and moisture vapor to escape to the outside. The first type of membrane is an air and vapor control layer, or AVCL, which is typically installed on the warm side of the insulation layer and is both air and vapor tight. The purpose of the AVCL is to limit the movement of moisture into the construction and also to reduce the air leakage rate, as we discussed earlier. To ensure it provides an effective and continuous layer, it's important that AVCLs are not damaged, so a reinforced material is desirable. Matching the vapor resistance of the AVCL to the building purpose is an important consideration to balance the need for walls and roofs to breathe against minimizing the condensation risk present. The dew point calculation allows this to be optimized according to project requirements. The second type of membrane, the vapor permeable membrane, allows the passage of moisture vapor but not liquid water. Vapor permeable membranes can either be air open or air tight, depending on the project requirements and membrane location. Because they do not trap moisture, they can be placed either outside the insulation or between insulation layers as required. If it's placed externally, it can also provide temporary weather protection during construction, while if placed over the shielding board, it can protect the panels or modules during transportation. As with AVCLs, it's important to verify the right balance of permeability is maintained throughout the construction, and there are two main methods of calculating this. The first of these, the Glaser method, as defined in BSEN ISO 13788, is a relatively simple means of modelling the flow of moisture in a steady-state condition, based on monthly averages of temperature and humidity. This straightforward method is sufficient to quickly assess most types of construction, and we have calculation software to provide this available on our website members area, along with U-value calculations. It's important to note that this method has some limitations though. Firstly, it does not account for the moisture storage capacity of materials, which can allow condensation to be stored and released safely. Secondly, it assumes moisture moves in one direction only, whereas in reality, the varying environmental conditions over an annual cycle will move moisture inwards as well as outwards. Finally, whilst it's possible to vary the preset temperature and humidity, it's not possible to model how these may vary over time, or to model performance over periods longer than a year. To fully and dynamically model these scenarios, the use of the BSEN 15026 method is more suitable. This provides a more complete analysis, but it is at the expense of requiring substantially more detailed and complex inputs. For this reason, it tends to be limited to more unusual or complex scenarios, such as the recently completed St Sidwell's Point Leisure Centre, where detailed environmental modelling and optimisation was a key part of achieving Passive House certification. Taken together, these tools provide a range of options to ensure the design strategy is matched to the outcome required, and the materials used are well suited to their specific application. In the case of a modular system, detailed analysis can confirm that a standardized construction can meet a broad range of application requirements. This process can also be used to develop a simplified range of configurations of panels and modules, each with a well-defined range of performance characteristics. Let's now look at how this approach can be applied to a modular system throughout the process. With the basic structure of the modules manufactured, building systems and services can be fitted out internally, with routing unaffected by any considerations around air barrier performance. An outer sheathing board such as our Proctor A1 cement board provides a solid substrate for the wrap-tight air barrier membrane to adhere to. These materials have also been tested as a system to verify both fire spread and through-wall fire resistance performance. Not only that, but Proctor A1 cement board can be scored and snapped, significantly speeding up the installation process. This method eliminates the need for ventilated cutting areas or mechanical saws, making it an ideal solution for a factory environment. Wrap-tight can then be used to wrap the entire module, providing a W1 rated weather-resistant layer, without compromising air leakage rates or the ability of the building to breathe. This negates the need to shrink wrap the modules during storage and transportation, both removing a process, a cost, and a potential point of failure should the wrapping become damaged. Depending on the required performance for the end use of the module, one of our range of vapor control membranes can be fitted internally if needed. We also supply a variety of accessories to accompany the wrap-tight air barrier to simplify sealing at openings and other penetrations. The corner sections shown help ensure continuity of the air barrier around the windows, which can reduce the need for additional gaskets and seals. There is also a wrap-tight split liner tape for use at corners and panel junctions, again aimed to reduce complexity during installation, whether on-site or off. This results in a weather-resistant module that can be transported and stored as needed, therefore final assembly on site. Any sealing of joints can then be done using wrap-tight tape and the wind and watertight structure pressure tested immediately, meaning any remediation can be assessed at the earliest stage possible. The final building can then be completed with the air barrier in place and tested. We can also supply the wrap-tight UV membrane, which delivers all the benefits of wrap-tight but with ultraviolet resistance for use with open-jointed cladding. Similarly, while wrap-tight can be used in warm pitched roof applications, we also have our Proctor air underlay membrane, which is both air and vapor permeable for optimal performance in cold roof build-ups. That concludes today's webinar, and we'll now move on to the Q&A session. So I think I'm going to make a quick suggestion here. The live link can remain the same. If people want to go and grab a cup of tea and hopefully come back in 5 minutes or so, but they can't hear me. Oh, can
Basil's just
anyone hear
saying,
me now?
yay.
Is
On
that
now?
working now?
Yes, according to the feed.
Okay. Oh man, okay. At least people know it's really live, and these teething problems do happy. I'd done the team are working on it, and then I realized it would be back to front, so it wasn't going to work anyway. Right, I'm so sorry about that. We don't know what went wrong. Thank you for those of you that hang on. So I'll make this intro very, very quick, and then we'll get straight on to the questions. So thank you all for attending. Appreciate that you've joined us and the patience with the sound issues there. We have almost 250,000 views of our webinars to date. No sound issues until today, which is a bit frustrating, but hey ho, there we go. Thank you, marketing, for sorting that out quickly. So if you have a question, please post it in the same feed where you've all been telling us that we didn't have any sound. So no problems with that. And you can email us at webinar@proctorgroup.com or direct message us on social media channels at proctorgroup.com. If you go to our webinar page, proctorgroup.com/webinar, you can find everything you need on there, request a meeting. You can still sign up for the webinar and get a replay to watch it back, etc. If you enjoyed it, give us a thumbs up, or you can subscribe to our channel where you won't miss anything that's coming through it. Quick date for the diary, 25th of July will be our next webinar, which I'm hoping will be sound issue free, topic to be confirmed in the next couple of weeks. So this week, our panel of individuals for the Q&A, a couple of familiar faces. We have Adam Salt, who is our Head of Global Sales Modular Offsite. Hi, Adam.
Morning, everyone.
Morning. Senior Technical Advisor Pamela Howitt. Morning, Pam.
Morning, everyone.
And a special guest, all the way from Brazil. So I believe it's early morning with you over there, Baz. We have Sebastiao Lima Neto, who is the CEO and founder of Dynamic 4. Morning, Baz.
Good morning.
Good morning. You could have got up a bit later, but great to have you here. So
Well,
just a quick intro to.
it's 3
Oh,
a.m.
sorry.
here. I'm actually in the United
Oh, is
States,
it?
but I'm from Brazil. So
Right. Okay. I did Google what time it was in Brazil. So 3 a.m. Goodness me. So you're just up from last night then?
Yep, kind of.
Okay. So just a quick intro to Dynamic 4 is a leading BIM consulting firm in South America that's been at the forefront of volumetric modular construction. So for nearly a decade, they've been collaborating very closely with manufacturing partners to drive innovation and efficiency in the industry. So thank you very much, Baz, for being here with us today. We really appreciate that. So I'm just going to go back on the feed to some of the earlier questions and start with you, Adam, please. Marina had asked, how can people become more on board with modular construction?
Oh, okay. Well, I think that there's lots of benefits to modular construction. But how can we get more people on board? Well, we can change some of the perception in the market, for one. I think every time there's a bit of negative press around modular, it tends to reach mainstream media, and everyone sees about it. But there's a lot of positivity that doesn't get noticed. So certainly the industry can come together and promote a lot of the positive projects. There are some companies all over the world doing fantastic things in modular, having lots of success, and offsite systems as well, not just full volumetric. But it is the future to construction. There's a lot more controlled environments within a factory compared to traditional build. You can enhance the inspections and the testings of those systems, looking at the way every aspect of that build is being built. So there's a number of benefits to that can reassure the market. I suppose people just need to get involved more and understand it. When I first joined the modular market, I had that negative impression of it that everyone else had. It was only once I actually started going to these companies and seeing some fantastic projects and examples within the factory that I became on board with it. And I think everyone else can do as well.
Thank you very much. And Baz, I'll come to you for the next question, please. I hope I'm saying that right, Baz. Greg Robertson has said, what does it take to build a module and what happens after it's built?
Well, that's a great question. We normally only see the product, the final product, and we don't see what happens in the backstage. to Adam's point, it takes a lot of effort in the pre-engineering part of the process. It's very important for us to design buildings that work from a modular construction standpoint, and not every building or project can be modular. So it takes a lot of pre-engineering, it takes a lot of coordination, because the output of coordination and design is the input for manufacturing. And that's where things start to fail. Basically, everything we fail to coordinate during design, we have to deal with during manufacturing. And that's why manufacturing can be so challenging. And it's very important for us. I always say that it's very important for us to start with the people. It's all about having the right people on board and considering not only the final product, but what it takes to get there.
That's a great point. Thank you. And Pam, Sharon has asked, what are the key considerations for ensuring airtightness in modular buildings?
I was just about to speak and I'd forgotten I'd unmute to
Don't you
myself.
confuse us again now, Pam. That's dangerous. We've already confused me. No, go ahead.
Okay, so yeah, ensuring airtightness in modular buildings is in a way similar to what you would do in any other type of building. It's very much looking at the design, to look at how to minimize gaps in your penetrations and any sort of damage from fixings, holes, etc. And obviously ensuring that your design facilitates an accurate and continuous line for the vapor control or air barrier on the outside, depending on how you're installing it. So that leads on certainly onto materials. So things like wrap tight externally, wrapping the modules and then jointing them can make achieving that air tightness a lot easier and more robust and less prone to damage than perhaps doing an internal air tightness line. But like anything, it's all very much about the detailing and the installation. Badly installed products and components are always going to be a problem. Make sure that for example, the wrap tight is taped with essential overlaps and that there's no gapping, no holes, etc. Modular makes that kind of easy because you can do that without interruption off-site, and you can make sure that it's good. You can even do some pre-completion testing before those modules even go to site, so that you know that you can remediate them and check them before they even leave the factory. So you're maintaining that quality all the way through the build.
Thank you very much, Pam. So I'm going to continue going through the YouTube feed on questions, and I do have more via email. So if you sent an email, please hold on. I am coming to you. I'm just getting through these for now. So Pam, if I can stick with you, could you just explain for Charles, please, a little more about what makes Proctor ProCheck Adapt different from standard vapor control layers?
Yeah, sure. So standard vapor control layers are usually a pure barrier. So traditionally, that was maybe something like an extruded polyethylene, so like a continuous layer of polythene. They then modified into membranes with reinforcement to make them more robust and to last the build process. And then over the last sort of 15, 20 years, the technology is looking at different things. And they launched or they looked at the technology using polymers that are adaptive, are intelligent. Basically, they vary with the temperature and humidity that is in the air. So with a product like ProCheck Adapt, it sits very nicely with natural fibers like mineral wool, hemp, wood fiber, that sort of natural materials that got a degree of moisture buffering. And the Adapt itself varies its vapor permeability or its vapor resistance depending on the climatic conditions. So for example, certainly in the UK, in our climate, which is a heating climate, in the summer when it's quite nice and warm, the air can hold more moisture, that product itself will become more vapor open. So it's almost like the pores open in it to allow two-way drying. So you get a lot of vapor movement in both directions through your wall. In the winter, when the vapor drive, and certainly in the UK, is generally from inside to out, that needs to be more vapor resistant, so more like a vapor control layer. And what happens is when the humidity is high and the temperature is low, and there's a greater risk of interstitial condensation, that membrane shuts up and acts at like a more traditional vapor control layer. So it basically allows you to get the best of both worlds. It is proofing your building and giving you a nice vapor permeable construction. As I say, it works very, very nicely with natural fibres, although it can be used with other more traditional insulation types.
Thanks, Pam. Baz, no one else can do the dynamic 4 question quite as good as you, I'm sure. So can you tell me, please, where does dynamic 4 fit in, and how can they help ensure efficiency and quality?
Well, that's a good question. To Pam's point, it's all about the detail and the coordination, and that takes knowledge and experience. Not everybody in our industry has construction experience. Anyone can learn the software or learn how to do something when it comes to the project, but having construction experience, that takes time. And we are here to bridge that gap and make that process seamless for everyone, especially to the GC, for the GC that normally has to handle all the issues and the inconsistencies on site. What we always say is garbage in, garbage out, right? And when we think about modular construction, the output of design is the input of manufacturing. So if a project is not properly coordinated, there will be issues during manufacturing and there will be issues during construction. That's where cost starts increasing exponentially. That's what we help to mitigate throughout the process by facilitating overall coordination, by working with architects, engineers, manufacturing partners, GCs, while ensuring quality towards deliverables and communication throughout the process.
Okay. And I mean, what kind of advice would you have for a developer or a GC is general contractor, I'm guessing, right?
Yes.
Yes. What kind of advice would you have for them if they're considering modular construction for their next project?
Start with the right people. People matter. So start with the right people, because if you don't have the right people on board from day one, your project will be much, much more complicated than it needs to be. And modular construction is complicated by nature because it taps into DFMA requirements, design for manufacturing and assembly requirements, and that's driven by the manufacturing partner you're working with. Each factory is different. They're not equal. They follow different standards. And if it's in a different country, it can get even more complicated. So having the right people on board will make the process much easier.
Okay, good advice. Adam, I'll come to on via email first and then another couple on the YouTube feed. Can you just go over some general challenges? So Joe has asked, what are some common challenges faced in modular construction and how can they be addressed?
I mean, there's challenges that are affecting construction in general. So that will apply to modular and traditional built construction, such as like planning, permission being delayed, etc. But some of the key ones maybe for modular design, I think one especially that we struggle with in the UK is logistics, trying to transport large modules. And that can be overcome. It just means real good planning, coordination with the right people, the right companies that, as Baz said, is experienced in dealing with a lot of those transporting of large systems. So it can be done, but that always tends to be a bit of a challenge, especially in the UK with our small, narrow roads. But we do find that in other parts of the world as well. You've then got compliance, especially with the regulations, trying to navigate different building codes. In the US, Baz will probably know this quite well. You'll have different codes for every state, different requirements, different approvals and acceptances. And that can also be similar to some degree in the UK as well, with local authorities maybe not understanding modular. So they need to get involved to ensure that compliance and understand it. And then I think the final thing is probably that the industry needs to overcome that perception and accept and get acceptance within modular. So to overcome those challenges, promote a lot of those positive aspects, get warranty providers more on board, get them understanding, get them into the factories to see how easy it is to inspect the build process. Yeah, that will help overcome that perception, really.
Okay. Someone just pinged a really good DM actually on my mobile here on Twitter. So Pam, if I can come to you, so in the back of what Adam's saying, this is from Amir. The wall thickness is vital to modular construction. So with the width limits on the back of lorries during transportation, are there ways we can reduce the wall thickness from the design?
Yes, so there is the possibility to do in your whole house or whole building analysis, there is the potential to look at trying to offset your air tightness against your U values. So what we're not seeing is purely insulate your unit or your modular or whatever building and increase the air tightness. What we're saying is make sure you have a good level of insulation there, so you know that that module will function, that unit building will function. But rather than just adding more and more thickness of insulation, because U values, we've touched on this in webinars before, it's a law of diminishing returns. It gets to the point where it gets unsustainable to continue to drop the U values, and certainly in the UK we're pretty much there. So we're having to look at using air tightness. So by improving your air tightness from say 7 or 5, which is actually a pretty leaky building, and a building that doesn't really take a lot of consideration beyond making sure you don't cut that square hole for that round pipe and leave it open. By dropping that air tightness level down to below 3, but even more down to below 1, down to sort of really sort of zero energy, zero carbon, passive house type standards, that will be able to offset the amount of insulation that you have to use. And also by a thin barrier, that air tightness line sub 1 millimeter will do more than potentially 40, 50, 60 millimeters of insulation. And there will be quite a bit of a cost saving in that as well, because insulation is not cheap, and structural elements to house it. So that's certainly one way of using it. Other ways to improve on a whole is also things like making sure you're doing a thermal bridge free design as much as possible as well, because if you put too many thermal bridges in there, then you have to compensate by increasing the insulation. So slim solutions with things like space therm as a co-bridging option is a good way of helping those bridging too.
Interesting. It's amazing what that airtight layer can offer actually when you think about it in terms of cost and carbon footprint, etc.
Absolutely.
Yeah, interesting. Again, I'll come to you, Adam, in a second. Just a quick one for Baz here. We had a question about digital twins. So can you just talk us through what are the benefits of building a digital twin and how can it impact overall quality towards deliverables?
Absolutely. So when you think about digital twins, it's very important for you to imagine a building that is being built before it's actually built. Sounds tricky. It's more complicated when you're building it. So what we try to do is build that model and make sure that we are assessing, reviewing, and conforming all the issues and inefficiencies that may cause rework during construction or manufacturing. Construction, like conventional construction, is more forgiving than modular, because if there's something that was not coordinated or if there is an issue, you will have to deal with that on the production floor, and it will repeat consistently 60, 100, 200 times. So the incurred cost is very high. The way we build our digital twin is to review and assess those issues ahead of manufacturing and construction, so they don't become a bottleneck during manufacturing. And then there's also something Adam said that is very important: procurement. If we have that information readily available in our model and we can perform simulations, then we can extract that information in such a manner that we can purchase and procure things ahead of time, and we don't have to deal with all the inefficiencies that we currently are experiencing here in the United States, and I imagine in the UK as well, with procuring certain products. It's not easy, And the last thing you want is to learn that your fan coil unit, for example, doesn't fit in the overhead space you have inside your dwelling unit. That just happens 200 times throughout the project. So building a digital twin allows us to ensure that level of efficiency and control that and confirm that in a safer space before we're actually dealing with that on the manufacturing floor or on the construction site.
Smart. And James Wilson has also asked Baz, how can BIM improve logistics, site planning, and execution overall? So where does BIM come into it?
That's a great question. Short answer is everything we fail to coordinate during design, we have to deal with during manufacturing and construction. So by implementing BIM, it's not just the software. When I say BIM, it's not like using Revit. It's not just about that. It goes back to having the right people on board. And again, garbage in, garbage out. When you have a solid process in place, it allows you to conform things ahead of time and use that for planning, scheduling, procurement, using the actual data that you extract from the model and procure. So it's much more reliable. It's much more predictable. You have that information in front of you. And if you need to perform simulations in your wall assemblies, in your floor assemblies, in your ceiling assemblies, it's all in front of you. So when the general contractor comes to you and say, hey, what would be the impact of using this fan coil unit over this one, or changing the insulation I have in all these walls, how much will this cost? You can easily look at your KPIs and get that information in seconds. And that's powerful, because if you have to go manually through the building and estimate how many walls you have, what's the overall impact, and what's the cost, it would take you days. And by doing what we do, you can do that in seconds.
Fantastic. Okay, I've got one more YouTube feed, then I'll start going through a couple of email ones. So Adam, Andrew's asked, how long can Wrap-Tite non-UV version be left exposed before installing external cladding?
Oh, that's a good question. I mean, with all membranes, you do want to kind of cover up as quickly as possible. You don't want to design them to really be left out there. But we understand that happens. Projects get delayed, and especially in modular construction, they can be stored outside for quite long periods of time. So we've gone through extensive testing with our membranes, in particular the Wrap-Tite and the Wrap-Tite UV. So we would always kind of recommend around 120 days, but our extensive testing has shown you can have Wrap-Tite exposed on a wall for up to 12 months and still be within specification. So you're covered kind of up to 12 months within the specification on a wall. And then for a roof detail, you're looking up to 6 months, a bit more onerous on the performance criteria for a roof. And then with the UV, if that is of interest, you're looking at 12 months straight up on that product.
Yeah, and I think also the climates that we've successfully been using Wrap-Tite and Wrap-Tite UV in, everywhere from sort of Arizona desert to the high humidity areas of Australia, etc. I mean, it's very much tried and tested.
Yeah, and I suppose also when we say experience and extensive testing, this isn't one test. This is 15 years worth of projects and testing and samples being sent to us from customers. Pam will know all about that.
Testing's still ongoing. We've got material in being aged at the moment, so we can carry out more testing. So it's a continuous process.
Yeah.
Fantastic. Well, coming on to that, Mark has asked as well, modules are designed to be manufactured and shipped straight to site. This hardly ever happens, so does that extended storage period lead to a number of design issues? So that's more of a general question around that. Pam, do you want to take that one?
Yeah, sure. They can cause problems, especially if you look at something we touched in the webinar. A lot of people will shrink wrap them. So basically that's putting a polyethylene, essentially vapor control layer on the outside, which means that if you've fitted the unit out quite extensively, you could have some wet trades. So what I'm saying is a lot will depend on how developed that unit is before it gets put together on site. If it's had, I mean, we have some projects or have had projects where skim, plaster, etc. Wet trades have gone on inside. So that's quite a lot of vapour that still needs to escape. By keeping the wrap tight as the external surface, that allows that unit still to dry out. But obviously, you've still got to remember that that unit is not in use, so it's not got occupancy coming in and out. It's probably not got whatever ventilation strategy put in place. So again, by shrink wrapping, you're creating something that could end up causing problems because it's trapping everything within the building.
Right.
So really, along with the side of exposure and making sure the detailing's right and making sure water's going to shed off, look at your detailing around penetrations. You might need additional little bits and pieces like liquid flashing just to make your design more robust. But by relying on the wrap tight as the external layer, which isn't going to go anywhere because it's fully adhered, you can cut out that shrink wrap. You can cut out that risk of that unit sweating. And might not be a big problem in the UK, but it could be a problem if you've got units going all over the world as well.
Yeah, during transportation, etc. Absolutely.
Absolutely.
Adam, this has come via DM. Can you ask Adam, I guess, because you are head of our modular offsite. All I'm hearing is negative stories from the modular sector. How are we meant to be confident that modular is the future of construction?
Yeah, I've touched on it already, but I think that it's crazy once you're involved in this industry how many positive projects and stories there actually are that just doesn't make the rest of even the industry news, let alone the mainstream media. We've got companies in the UK like Tide Construction and Vision Modular doing high-rise modular systems that is being looked at all over the world, going amazing. Elements Europe, Algeco, Starship Group. There's loads of examples that I could give. But yeah, it's great to see these success stories, but a lot of people don't hear about them. So I think that can be one of them. And then it's the governments as well. There are governments all over the world that recognise the benefits of modular construction. They're using it to tackle affordable housing. We've got cities within the US like Los Angeles and New York. They're using modular to combat the shortages and some of the homelessness they have within their cities. You've got countries in Asia that are adopting that sort of mechanical offsite install process and seeing the benefits of that. And a lot of it is driven from the governments. So I do inquire our government to do the same. But I wonder if Baz, you might have any ideas on how we can overcome those negative aspects as well.
Adam, I think you're tapping into a very important point. I mean, I think it boils down to how many units we need a year versus how many units we can actually produce. And we will never be able to catch up with the ever-growing demand for new units here in the United States or elsewhere. There are not enough factories, and our conventional construction, is not capable of supplying that with the level of accuracy that is required and affordability. So if you think about affordable housing, we don't see affordable housing anymore. So it's really hard for us to come up with a process that allows us to build affordable housing. Multifamily affordable housing is critical. We don't have, and our industry needs it. Our people need it. So when I look at that, I think that one of the ways for us to understand this is to understand reality itself. We need it. And conventional construction is not getting us there. Even modular construction is not getting us there. But we're learning as we go. The industry is relatively new. So there are a lot of automations that are kind of becoming part of the process. So we see lots of robotics associated with that, which is very important. And that's how I see the industry evolving and learning with the process itself and getting better. And again, I think that the best way for us to, get through it is accepting and embracing reality itself and the necessity for new homes, affordable homes, not just any home.
Yeah, I'd agree.
And Adam, I mean, can you tell us, how can modular construction be better than traditional built construction?
We actually got told a great example of this the other day. It's a controlled environment, and if you think about the manufacturing of a car, imagine someone came to your house and dropped off the engine one day, dropped off the bodywork another day, and it slowly got put together on your driveway over a space of a couple of months. You'd be like, why? I can just go to the dealership and pick one that's been made in a factory. So that kind of, with that analogy, that kind of shows where modular makes sense. The only thing I don't like about it is when we get to the end of a modular line, that isn't the finished construction like it is with a car when it gets to the end of the factory line. But it still does make a lot of sense to move it into a controlled environment, move it into an area we can regulate it better. I mean, if you're going to inspect a building site now of 100 homes, are you going around every aspect of that home for all 100? No. If you're going into a factory to view the constant line, you are, especially on a rainy day, you can stand inside as well. So that just makes so much sense. It's precision built as well. You should start to get better performances. So where we're trying to move with our regulations to achieve passive house standards or better, then we're needing to be in a better environment to actually create that. Sometimes it's not the products, it's the install of those products that achieve those performances. And in a factory just makes so much more sense to me to do that.
Yeah. And Paul has asked, I mean, what do you think, Adam, about the principle of design for manufacturing and assembly? So DFMA, which we touched on during the webinar. I mean, how does that help in modular construction?
Yeah, I mean, it's going to simplify and streamline that design by considering the actual process of the fabrication. So, the designer's goals and requirements are going to be met by almost designing out those opportunities for problems that to arise. So yeah, you're then going to get standardization, repeatability within that manufacturing process, and it's all just going to become a lot more of a smoother process. And Wraptite fits in quite well with DFMA as a product. It aims to simplify achieving those low targets, which simplifying that process fits in really nicely as well.
Good. Conscious that we're reaching the hour, and obviously we wasted a bit of time at the start. I've got a few more questions just through via email, and one on YouTube. So if I come to the email first, Pam, could you answer Jerry's question, please? How does future potential amendments to a modular building, so like for example, extensions, forming new windows and doors, etc., impact the performance of the structure in regards to airtightness? So if you're altering that where Wraptite's been applied, does that damage the product? How do you navigate around that?
I think a lot will depend on what extent you're going with. And like anything, if you're replacing, shifting, there is always the risk of damaging. However, if you're taking a window out and you've damaged that membrane, you can actually go back in and retrospectively remediate that before you continue with your windows. Windows and doors may not be so critical because you're going to be putting in some sort of interfacing system like an EPDM or some sort of flashing unit which can seal, so that might allow you a little bit of flexibility in that. But you can layer up, because Wraptite is a permeable product, you can layer up several layers, quite a few layers, before you start noticing any compromise to that. In terms of adding extensions, again, that can be done. I mean, Adam and I visited a site where they're looking at sort of modular off units for hub buildings with the intention that the end can be taken off, new modules slotted in, and the end put back on again. Now, the beauty about Wraptite is because it's vapor permeable, you could actually just take that new extension unit and essentially plug it into the end of the building or wherever you're needing to accommodate that. And it's not going to trap moisture like a traditional vapor control layer because it allows that vapor movement in both directions. So that means that you're reducing the risk, but also because the membrane is on the outside, most of these will be cut in from the outside. Cladding, brickwork, etc., will be taken off. so you can still get in and remediate and join those junctions. So there's definitely ways of doing it. A lot will depend on the system and whether it's intended for that modular modification during the future of it. But it certainly is easier to successfully junction an extension into an externally applied membrane than it would be if you were trying to do it with a vapor control layer inside.
Absolutely, I completely agree. And one on the YouTube feed from Scotty W. Does the UK's insistence of cavities in walls make offsite solutions more complicated to adopt? Pam, is that one, or Adam, perhaps? One of you guys help with that one?
Go on, Pam.
I mean, is there
Well,
insistence
yeah,
in
it's a difficult one. I get the point. I mean, I've seen a lot of modules going out to site with cavities on them. So, you have battens and the rain screen system or brick slip system on them. So that's not really affecting the ability to do that on site. And we're also seeing a lot more with external wall insulation on buildings as a whole. So again, that's a building done without a cavity. So, I mean, Adam, I don't know what you're seeing elsewhere, but I don't envisage it being a challenge. I think there are options.
I think the UK does love a brick and block cavity wall build-up. That is very well known. With the improvement of regulation requirements, we are now seeing a huge increase in offsite because it kind of is the only way to go forward with it. Timber frame is increasing massively. For example, steel frame as well. So it is coming. What is great though is the innovation that we're seeing. Some of the brick slip systems now, for example, you can barely tell the difference between that and a brick built wall. So that's encouraging that there's innovation to overcome that. But yeah, I do understand that we do love a brick and block wall in the UK.
Certainly do. Certainly do. Right, last couple of questions, because again, I'm conscious of time. Baz, I mean, can you just talk us through, I mean, what technologies should we be seeking when we're implementing things like BIM? I mean, what technologies should we all be thinking about in this sector?
Well, that's a great question. I think that the first thing you need to consider is your objective with BIM. Like, what are you trying to accomplish? So and who's your client? Like, who's your target? We work with factories here in the United States and Canada, and for some of these factories, what matters is a shop drawing package. So what they will need is a PDF with all the drawings so they can follow and execute that based on everything that has already been coordinated. We also work with other factories that they need something more substantial, and they ask for AR and VR models, and they use that for training, for coordination, for QC. So if they're on the production floor, they all carry tablets. So if they're on the production floor, they can easily inspect a wall assembly and use the AR model to see if everything that was built is meeting all the specifications and requirements that were considered during design. So if we did it the second with the first factory, it would probably fail because their objective is not to have AR and VR technologies associated with the process. So it's about understanding what requirements you have and what's your objective. But at the end of the day, what I always encourage our clients to do is try to simplify the process and not overcomplicate it, especially if you don't have the means and methods to execute. So try to understand what your critical what is the critical importance for you when you're doing what you're doing, and start with that. Then look for the right people that can facilitate the process, and then start thinking about processes that you need to implement to execute and complete that task, or build a module or anything else you're trying to accomplish. And then you consider technologies. So technologies is normally the last thing we consider. And as I always say, try to simplify, not complicate the process.
Very much. Adam, a last kind of environmental one for you. Can you tell us some of the environmental benefits Lee has asked by email of modular construction?
Interesting, because I was at the UK Construction Week the other day on the MPBA panel talking about this very topic. Yeah, I mean, there's a number of benefits. Reduce waste being the main one. When you're in a factory, you should generate less waste. It's more precision made. Cutting of the membrane, for example, it can be more precise and hopefully designed a lot better to not increase your waste. There's also then the kind of in application of these projects, we're hoping that these modules are more energy efficient. So that's going to improve the environmental benefits because they've been better built, so lowering the overall carbon footprint. But interesting, I think also we're looking at EPDs for products within build-ups. Well, we can start to look at now EPDs of modular systems. So the whole system can have an EPD as well, which will help us understand the life cycle assessment of that system for calculating on our projects, which sometimes the on-site in traditional build can go amiss because we're just looking at the products and how they're included. So you should get a more in-depth understanding of that environmental performance as well.
Thank you. Great. Okay. Well, no more questions I can see coming through. So I just want to thank everybody for joining and your patience at the start. And I'd like to personally apologize to the team if I just checked my Teams or my WhatsApps instead of talking through with no sound or the YouTube feed. Thanks to the audience who were trying to inform me. Then I could have saved a little bit of time for people and I wouldn't have been talking in silence. So thanks again for that. And again, apologies for the glitch at the beginning. Baz, thank you so much for joining us. I'm guessing you must be kind of West or Midwest if it's the middle of the night for you. So we really appreciate it. Thanks for your time. And Adam and Pam, thank you. And Adam and Pam, thank you as always for your input and expertise. And, you know, the audience, thanks for attending. We wouldn't be doing these if it wasn't for you and for the questions coming through. I love the quality of the questions we get via email on the YouTube feed and the DMs. It really helps make a good topic discussion. So date for the diary, 25th of July, Friday at 10 a.m. I promise that the sound will work at the beginning. And we're kind of throwing about some topics at the moment. Obviously, it will be in Proctor style based in construction, but we will let you know that within the next couple of weeks. So it's really important that you subscribe on our webinar page for future updates and to our channel, and you'll see what we've got coming ahead. So if you need anything, please contact the team via that page. You can book a meeting, you can contact our technical team, which Pam obviously sits within, and they're answering questions or anything you need. So it helps us if you do a thumbs up if you enjoyed today, subscribe to our channel, and we hope to see you on the 25th of July. And thank you for attending and have a lovely weekend.
Thank you.
Thanks, everyone. Bye.